Hey kids, welcome back to our next class of Catalyst. So until now, we have looked at refraction as a concept in a certain manner. We've looked at some experiments, we've looked at some bit of theory. We also looked at something called total internal reflection, if you remember, right? So today what we are going to do, we're going to look at the different values that we find within this chapter, refraction, and how they relate to each other, right? How are they connected to each other? So we'll quickly just recap few of the concepts that we've learned so far. So we know that refraction happens whenever there is a shift in the medium in which light is traveling. Say for example, this is a surface of a medium and light goes in, right? This becomes the incident ray. And then this is like the normal at a certain point of incidence, right? If this is a rare medium and this is a dense medium, then what happens is this ray of light refracts and moves closer to the uh, normal, right? So basically what that is says is this angle of incidence, this should technically be I, and this angle of refraction, right? It's not reflection, the difference being refraction. When light goes from rare to dense, this angle will reduce. I is greater than R. And the opposite is true for dense to rare, right? So if it's going from a dense medium to a rare medium through a point, maybe like this, right? So this angle will be I, but R is going to be much bigger, right? This is what we have looked at so far. And we have also seen that at a certain angle of incidence, whenever light is going from a dense to rare medium only, total internal refraction will happen. Reflection happens. Basically, the light kind of bounces back, goes back into the dense medium. We've seen this in the activity in our previous class. So what are these values and how are they related? If you recall, we have also looked at something called refractive index, right? We've seen absolute refractive index and we have seen relative refractive index. So for refractive index, we denote it by the alphabet N, right? N1 for the first medium, N2 for the second medium. Now, each medium has its own refractive index. So for rare, let's say it's N1 over here, sorry, N1, right? So N1 and this one will have N2. Now, if you see the angles I and R, for N1, the angle is I, right? And for N2, the angle is R, related to the medium. Incidence is from the rare medium and refraction is through the dense medium. So there is sort of a connection over here with the angle and the refractive index. Now, what that connection is simply when you go ahead in math in the next year or so, you're going to read about something called as sine. Okay, sine is nothing but a function that we can use on an angle. Okay, it's used in trigonometry, triangles. Basically, it's just something that will be used on an angle. What it is, it's not important right now, which you're going to learn anyway. Just know that we use it on angles. Okay. Now, I can say that sine can be used on this angle of incidence. It can also be used on angle of refraction. Okay. Now, since n1 is related to I can say that n1 multiplied by sine of I. Okay, sine I is one value on its own, will be equal to n2 into sine of R. Okay, with each mediums, the sine of its angle. All right. So if I want to make a crisscross reciprocal, you know how to do that, right? So I'll shift n2 here. So that should become n1 divided by n2 equals to sine R divided by sine I. Okay, it means the same thing. There's no difference as such. You can use it in any form. Okay. Now, if I have to reciprocal this, I'll say n2 divided by n1 equals to sine I divided by sine R. Now, all of these are the same thing, just different ways will help us calculate sums in a different manner. You don't need to remember all. Long as you remember the main one, you should be good to go. Okay. Now, this is what we call as Snell's law. Okay. Snell is the name of a scientist, and he was the one who founded this law. So we call it Snell's law. So this is the statement for Snell's law. So the ratio of the refractive indices of the mediums will be equal to the ratio of the angles of incidence of and refraction. Okay. Sometimes it's also used with velocity. That will basically be the speed. Okay. So for velocity, we can write it as v1 by v2 equals to sine I divided by sine R. Depending on what the sum is like, we can use any of these formulae to solve the sum. Now, we know that total internal reflection happens only when we go from a dense medium to a rare medium, right? So for the reference, I'm just going to keep it over here, one diagram. We're going from a dense medium I to a rare medium, right? Dense and rare. Okay. So over here, N1 is for a dense medium and N2 is the index for the rare medium. What if I use Snell's law in this, but only in case of total internal reflection, right? So we remember total internal reflection happens something like this. The light comes in, touches the surface, but it bounces back, right? One interesting thing about this is when total internal reflection happens, this entire angle would be about 90 degrees, right? So the angle of refraction would be 90 degrees. Something to keep in mind. Why? I'll tell you. Now, we know from Snell's law that n1 by n2 will be equals to sine R by sine I, right? Now, n1 and n2 we already know is nothing but the refractive index. But in the case of total internal reflection, we know that there is something called as critical angle, right? That is a minimum angle required for total internal reflection to happen. So for this critical angle, I will call I as nothing but C. Okay, this C is nothing but critical angle. and my R, my angle of refraction will be 90 degrees. Okay, because that's the angle at which it will refract in total internal reflection. So if I use these two values in the formula above, I should get N1 by N2 equals to sine 90 divided by sine C. Okay, little mistake, divided by sine C. Since you don't know trigonometry, there's one thing that where sine C is nothing but 90 degrees. Okay, so sorry, sine 90 is nothing but 1. So N1 by N2 equals to 1 by sine C. So sine values start from 0, go up till 1. Okay, sine 0 is 0 and sine 90 is 1. After that, it will reduce again. All right, so now I can tell that sine C can be reciprocal. So if I have to reciprocal this, I can write it something like this. Sine C equals to N2 divided by N1. Okay. Now, this is one way that we can write this relation between total critical angle and the refractive indices, but there is also another way that we can put it. So I can write sine C as 1 by N1 by N2, right? I take that N2 all the way to the bottom and make it N1 by N2. So if you remember, N12 is nothing but N1 by N2, that is relative refractive index, relative refractive index of first medium with respect to second medium. So that is basically from the dense one to the rare one, right? So I can write this as sine C equals to 1 by N12. Okay, I can also write this as sine C equals to n to 1, since n2 by n1 is nothing but n to 1. But generally, when we have to solve for problems, they'll ask us for, and they'll give us n12 or they'll ask us for n12. So both of these formulae will come in handy. All right. So this is how total internal reflection and critical angle and Snell's law, right? This is the connection between all three of these different concepts that we can use whenever we are doing questions. So going forward, we'll also have numericals. So I'll show you examples of what they can ask and how do we solve them using these formulae going forward. Okay, so that's it for today. I hope you understood and I hope you had fun. We'll see you in the next class with a couple of more questions. All right. You have any questions, doubts, please drop them in the comment box below and I'll see you in the next one.